right, welcome to Module 14, Lesson 1, which is volcanoes. So just to review, most volcanoes occur at convergent boundaries, which are boundaries that come together. So they're plate boundaries that collide. And volcanism is just referring to any kind of magma or lava that comes above the surface. So magma is underground, lava is above ground. So anytime that magma reaches the surface, it's considered to be volcanism. It doesn't have to be a big peaked volcano in order to be considered a volcano. It's just whenever magma comes above the ground. So if we look at this map, here is all the different areas that are volcanoes. So this is the Ring of Fire. And so all of these volcanoes occur, most of the active volcanoes on the Earth occur along this Pacific Ring of Fire. And this is called the Circum-Pacific Belt, which is also known as the Ring of Fire. And then you've got a few other places where we have volcanoes, but the majority of them occur along that Ring of Fire. All right, and then if we look here, we've got a convergent plate boundary. So we've got an ocean plate colliding with a continental plate. The ocean plate is subducting because it's more dense, and that brings down with it water, and water reduces the melting temperature, which creates magma that rises and forms volcanoes like Lassen and Shasta. And most of those volcanoes, most land volcanoes occur at convergent plate boundaries where we have subduction occurring.
White Island, as with all of New Zealand, sits right on the rim at the junction of the Pacific and Australian plates. It's a collision area where the floor of the Pacific Ocean dives deep below the Australian plate in what is called a subduction zone. The seafloor is buckled and pulled down into deep trenches, and the friction triggers powerful earthquakes as the Pacific plate is slowly consumed. Even here, magma flows from underwater volcanoes as rocks are melted and recycled. White Island is one of a chain of volcanoes that includes the notorious Tarawera.
That was quite a bumpy flight. But it's worth it because we're right on the Pacific Rim there, aren't we?
We are. This is the Pacific Ring of Fire at its best. There aren't many places where you can see it so graphically.
So we're literally walking to the edge of the Australian plate, and right in front of us is the Pacific plate.
Well, not quite going that far. I mean, we really are entirely on the Australian plate here. But this is where we feel the effects of the downgoing Pacific plate.
All right, so on to the next one here. All right, so if we look at this Ring of Fire, we have the what's called the Circum-Pacific Belt. And so most of our volcanoes occur along here. And this is also the plate boundary. So this is the Pacific plate. And this is where we have that Ring of Fire because all of this Pacific plate is subducting underneath the rest of the other plates. All right, and then we have some other smaller belts, but we have the Mediterranean belt. And so here's the Mediterranean Sea, and you can see, let's see here, smaller. So we can see here that this is another small belt that creates those Swiss Alps and mountains that are in Europe. And so you can see there's a lot of earthquakes and volcanoes. And earthquakes always occur where there's plate boundaries as well because the plates are moving there. All right, so divergent plates are moving apart. And so we do have volcanism where divergent plates are occurring. So this would mostly be along the mid-ocean ridge and then also in Iceland. So Iceland is the one of a few places on Earth that the mid-ocean ridge comes up onto the land. And so as the plates move apart, Iceland is actually growing and getting bigger, but it's known for a lot of volcanism because of that. And there's a type of magma that comes up. It's called pillow lava. So it looks like pillows kind of forming. It's kind of cool.
But while some plates crash together, others tear apart. It happens under the ocean. Like here, in the middle of the Atlantic. Lava erupts at the boundary between two crustal plates, sealing the tear. This is the Mid-Atlantic Ridge, a 10,000-mile tear on the floor of the Atlantic Ocean. The ridge is a line of underwater volcanoes, and it's here that new oceanic crust is formed. It stretches from the South Atlantic all the way to Iceland in the north, where it rises above sea level. From the air, the Mid-Atlantic Ridge is an awesome sight. This dramatic scar in the landscape marks the boundary between the North American crustal plate on the left side and the European plate on the right. The gap between ocean plates is filling in at a rate of an inch a year. Part of the restless movement of the Earth's crust that's reshaping our world.
All right, so that was Poa lava. And so here we've got hotspots. So hotspots are how the Hawaiian Islands have formed. And hotspots are where we've got a weakened area in the crust and magma rises up in that weakened area and creates volcanoes. So the hotspot's occurring under the crust. So the crust moves along, but the magma, the hotspot remains. And so it creates chains of islands like Hawaii. All right, so here we can see the direction of the plate movement. So this is the Pacific plate here. So the Pacific plate is moving up in this direction. And so notice how here's the current Hawaiian Islands, but you can see a whole bunch of islands that some of them used to be above water, some of them never were above water, but they are this huge chain that shows the direction of the plate moving. Currently right now, the big island, Hawaii, is over the hotspot. So that's why Kilauea, for example, is erupting right now. So it's been erupting since 1984, but it erupts off and on. So it just started last, maybe a couple weeks ago now. But anyways, so that's over the hotspot. And so eventually Hawaii will move off the hotspot and another island is actually starting to form right now. And that's just kind of to the south of the big island. And eventually Hawaii, when it moves off of that hotspot, will be dead as far as magma reaching the surface. And so then the other island maybe will become an island. That's only if it goes above the water. But otherwise it will just be another volcano. All right, so the hotspots show the chains of motion. So as the plate moves, the hotspot stays there, but the chains of islands continue. So just know that Hawaii was formed by a hotspot. And we can also measure the rate that the plate is moving by looking at the age of the rocks and seeing how old the lava formations are on the islands, and we can determine how fast the plate is actually moving.
Volcanoes usually occur at plate boundaries, where the continents collide. When they hit, they release unimaginable energy, punching up molten rock from deep inside the Earth. The Pacific Ring of Fire marks a whole series of these plate edges. It's got half the world's active volcanoes. Hawaii is more than 2,000 miles from the nearest collision zone. Beneath the ocean floor is a mysterious area of super hot liquid rock. Hot enough to melt a hole through the Pacific plate, punching up fresh lava. It's called a hot spot. The ocean floor is creeping gradually northwest at 3 inches a year, but the hot spot under it doesn't move. A volcanic island builds up, but as it moves away from the hot spot, it is cut off from the source of lava and dies. Over the hot spot, a new volcano forms. But if the big island is growing, then what's happening to the island of Oahu? Oahu should be shield-shaped, circular, but it's not. It's long and thin. There's a chunk of it missing. All that's left are 1,000-foot-high cliffs.
Because you can obviously tell that this isn't a shield volcano anymore, that there's something definitely missing from this spot.
As the water turns the rock to soil, the cracks burrow even deeper. A fatal weak spot develops until one day, it all just lets go. This cliff is a crack, 1,000 feet deep. Based on the shape of Oahu and the height of the cliffs, Lloyd estimates the land used to extend out from here for another 20 miles.
All this used to be solid rock. And all that rock disappeared to the ocean below.
Two million years ago, the island fell apart. 300 square miles, 20 trillion tons of rock dumped in the Pacific Ocean. That's why Oahu has an unusual shape. The rock slide really has taken a bite out of the island.
All right, so looking at here, here is what we call flood basalt. So they're basically fissures, so openings in the Earth's crust, and then they form basalt kind of lakes. And so those would be these areas in Washington and Oregon that have formed because of cracks in the Earth's crust. So this basalt has seeped up from ocean rock. All right, and so so we have other places in the Earth where we have these flood basalts as well, but just know that they form from fissures in the crust.
2-minute geology, 2-minute geology. Hello, young people. The Columbia River basalts near Quincy, Washington. We're at Quincy, Washington, but we could pick any spot between Spokane, Washington, and Seaside, Oregon to do this show. These brown layers of basalt are everywhere in the place where the Ice Age floods did massive amounts of erosion thousands of years ago. There's more than 300 layers of basalt here, 300 separate volcanic eruptions, and the stack of basalt is more than 2 miles thick in places. The lavas started erupting 17 million years ago here and flooded a landscape, buried a landscape in lava. The obvious question is, which volcano erupted? Was it Mount Rainier? Mount St. Helens? The answer is none of those. The Cascade volcanoes do not match the chemistry of these basalt lavas. These are lavas that came from the east. They erupted out of fissures, deep cracks that emitted Hawaiian-like lava starting 17 million years ago. Fissures that formed related to the birth of a hotspot that's now underneath Yellowstone National Park in Wyoming. The present is the key to the past. To really visualize Eastern Washington 17 million years ago, we need to go to Hawaii today. Those Hawaiian lavas today are the same kinds of lavas that we have here. Lava flows in Hawaii, very fluid. The most fluid lavas we have in nature average less than 3 feet thick. Here in Eastern Washington, the lava flows average 100 feet thick. In Hawaii, the lavas travel on average 3 miles in length. Here in Eastern Washington, many of the lava flows traveled 300 miles. And in Hawaii, 30 miles are covered by a typical flow. Here in Eastern Washington, 30,000 square miles of area buried. The Columbia River basalts near Quincy, Washington. It's all out here to see. Cooley's rocks and canyons is scenery. here for you and me.
All right, so magma reaches the surface and it travels through chambers. And these chambers are called vents. And so venting is where it comes out of the surface. But these conduits are where it flows through. And then, like I said, it emerges out of the vent. And that vent, it continues to build up as layers and layers. And you can see the layers here are flowing out and covering the area. So it continues to grow in size because of that. All right. So over time, it forms the different layers, which forms a volcano, and then eventually it could form the crater. So the crater would be at the top, and you can see there's a crater here too. So anywhere where you have magma coming out and hollowing out an area could form a crater. And then we have something called a caldera, and so a caldera is where a crater has collapsed. So there could be a caldera up here if, as it's venting and moving out, this area kind of collapses in on itself, especially as it's cooling. So that can form this big caldera. So a really good example of a caldera is Crater Lake. So Crater Lake is a huge caldera. It actually has a smaller volcano inside of it called Wizard Island. But this is a huge caldera. And then it's just rain filled. So it's water filled from the rain. And that's what forms the lake on top. And it happens to be a perfect caldera with no outlets. And so that's how it formed a lake. All right, so the way volcanoes look are for two reasons. So it depends on how it erupts. So there's a couple different ways that volcanoes erupt. And we'll talk about those in a minute. There's three types of volcanoes. There's shield, cinder, and composite. So if we look at a shield volcano is very flat, kind of like a shield. So you can picture a shield kind of being laid on its side. So a good example of these are the Hawaiian Islands. So they don't look like big, huge peaks like Shasta and Lassen, but they're very wide, broad-based volcanoes. And then cinder cones are just kind of cindery material. So they're forming with not a lot of force. I mean, they do erupt semi-explosively, but they are made mostly of tephra, which is a cooled material. So it's magma that kind of cools in the air and forms this cindery layers. And those are cinder cones. And then the last type is composite. So composite are formed from layers of lava and then layers of explosive tephra. So it's kind of like a combination of both, I guess. But anyways, there are layers of explosive volcano eruptions followed by layers of lava flow. So think of Mount St. Helens, for example, erupting explosively, and then lava seeps down over the sides, causes it to grow, and then maybe another 1,100 years later, it erupts again, and same thing occurs. So they tend to be our tallest. They're also our most dangerous type. So composite, our tallest and most dangerous type of volcano because they're very explosive.
You probably have a pretty good idea what this is. It's a volcano, a place where molten rock called magma from deep within the earth makes its way up and erupts at the surface. But what you may not know is that not all volcanoes are made in exactly the same way. In fact, they come in a variety of different shapes and sizes. Here are the three main types of volcanoes. The smallest type of volcano is the cinder cone. Cinder cones form when thin or runny magma is flung in the air during an eruption and then hardens and falls back to Earth in fragments called cinders. Over time, these cinders build up, creating a cone-shaped mound. Cinder cones can form rapidly and are the shortest-lived volcanoes. A famous one is the Paricutin volcano, which formed in a Mexican cornfield in 1943. It was active for only 9 years, but in that time, it transformed what was once farmland into a 1,200-foot-high peak, destroying 2 villages in the process. The largest type of volcano is the shield volcano. These volcanoes pour out very runny lava flows, which can travel many miles. When the flows cool, they form thin sheets. These sheets build up to form a wide dome that resembles a warrior's shield. Despite their size, they're actually the gentlest volcanoes. In fact, tourists can actually watch the slow flow of lava from the shield volcanoes that form the Hawaiian Islands. The most common type of volcano is the composite or stratovolcano. These are what most people think of when they imagine volcanoes. They usually come in groups of volcanoes all aligned in a chain. They're formed from alternating lava flows and layers of hardened particles called tephra that are flung out of the volcano during an eruption. Composite volcanoes have the most violent eruptions because the lava they eject is stickier or more viscous than the lava from cinder cones or shield volcanoes. As a result, more pressure builds up in the volcano before an eruption. Some composite volcanoes have what's known as a lava dome at the top, often within the volcanic crater. These form when thick, very viscous lava gets pushed up over the vent like toothpaste and hardens, creating a sort of lid on the volcano. Volcanoes with lava domes have very forceful eruptions because the magma has to push its way through the lid. Mount St. Helens famously grew a lava dome in the crater that formed during the 1980 eruption. These are the three main types of volcanoes, but there's plenty more explosive science to discover.